Hello. Good morning. Good morning. Hope everybody's doing okay. I feel like I was just here because we did this last night instead of Monday this week. So we're going to finish up the packet today, and we're going to talk about density and moles. And perhaps the most important thing to know about those two things is that um, the the techniques we're going to use to solve the problems are not different from what we just did last night with unit conversions. So if you feel comfortable with unit conversions, density and moles should fall right in there. We're just going to be using some different numbers and some different conversion factors, but that's really, we can think of them in the same way. So when we talk about density, let's first just talk about it conceptually. Which weighs more, a ton of bricks or a ton of feathers? Well, a ton is a measure of mass or of weight, so they're the same, right? You have the same weight of two things. Doesn't matter what it's made out of, same weight is the same weight. That's why, like in lab, we use the balance so much. It's a really good way of measuring things regardless of the content. Would a ton of bricks take up the same amount of space as a ton of feathers? Not really a circling type question, so I'm going to cross that out. But no, it would not take up the same amount of space, right? The feathers, if you have the same weight, the feathers would take up a lot more space. And so that's an issue of density. So we might say that the bricks are much more dense than the feathers. So a general equation for density is mass divided by volume. So if we want to express it as an equation, it might be like this: density equals mass divided by volume. So if we think about this then in what we did last night, what this really is a conversion factor. It's mass per volume. Just like miles per gallon, we might have grams per milliliter. So we can use density as a conversion factor, and that's how we will be using it primarily in these questions. But first, let's just calculate some density. So density units will always be a mass per a volume. Sometimes that volume is expressed in milliliters or liters, and sometimes it's expressed in cubic centimeters. A cubic centimeter is a cube that is 1 centimeter on each side of the cube. And so that actually is the same amount of volume as a milliliter. So remember that little conversion there. It's an easy one because we don't have to change any numbers around, but we have to remember that a milliliter is equivalent to a cubic centimeter in volume. So there are lots of different units. We could do grams per milliliter, as we just talked about. We could talk about grams per cubic centimeter. We could talk about kilograms per liter, or sometimes with gases, we want a much smaller density, grams per liter instead of just grams per milliliter. You could also use density in the English system, something like pounds per gallon would be appropriate, or trying to think if there's another common one, pounds per cubic inch or pounds per cubic foot, something like that. All right, so let's calculate some density. Now, you're going to do this in the virtual lab this week if you haven't already, or next week, depending on your lab schedule. But basically, a good way to measure volume of an object is to put it in water. And you did this in the measurement lab early on in the semester, where you take an object and you submerge it in water in a graduated cylinder, and you watch for the difference in volume between where the liquid started at and then where it ended at after the object is in there. And that gives you a measure of the volume. And that's generally more precise than trying to actually measure the object on all its sides, unless it is a very, very clearly, like a cube or something. If it's any sort of irregular shape, you pretty much have to do it by displacement. So a piece of gold weighs this, and that is the mass of the gold, 497.94 grams. What is the volume of the gold? Well, let's see. It's placed into 41.1 milliliters of acetone. Then it sinks, and then the level of the acetone is raised to 66.9. So the difference between those two numbers, where the amount of acetone that starts and then where it's raised up to, is going to be the volume of the gold. So in this case, that would be 25.8 milliliters, I think, if I did that right. So then the density is the ratio of mass to volume, or mass divided by volume. So we can calculate this. 497.97 divided by 25.8 is 19.3. And now our unit is going to be grams per milliliter. We can write like that. And that's our density. Okay, so now let's use density as a conversion factor and do a similar calculation. So in the next problem, what would the mass of 25 milliliters of milk be if the density of milk is 1.034 grams per milliliter? So again, just like the problems last night, we're starting with a certain amount of milk, and we want ultimately to get mass. So we want to go from milliliters, which we started with, to grams. And we're going to do that via a conversion factor, 1.034 grams per milliliter. So that would look like this: 25 milliliters times the conversion factor that converts milliliters to grams. Right, so we're going to cancel milliliters, end up with grams, which is what we want because the question is asking for what would the mass be. All right, so then we fill in our numbers using the density. The density is 1.034 grams per milliliter. And so then our answer for mass of milk would be 25.85 grams. We could round that up to 26 if we wanted to just keep the two significant figures. All right, so this one, the next one I'm going to let you do on your own, but definitely come back and ask if you're having trouble with it. In this case, we have to do a couple conversions first before we can use the density because we are being given a quantity in liters, and we're asked for an answer in kilograms. But then the density is given to us in grams per cubic centimeter, which we can also think of as grams per milliliter. So we've got grams and milliliters in our density conversion factor, and then liters and kilograms. And you can do some conversions there. You may also find a little shortcut there. But give that one a try and see how it goes. All right. The next topic for this morning is the mole. And we're going to start with a little blank space here so I can write some stuff down. Sorry, okay. Now, the mole is a number, and you may have heard of it before in relation to chemistry. You may have learned about it, or you didn't quite get it before. But we're going to relate it to a couple other common numbers that have a name. So one that we know is a pair. Probably heard that before. One pair is 2, right? 2 things. 1 dozen is 12. And notice there's no unit here. We could say items or whatever it is that we're counting. It's just a way of counting things in batches, in large batches, rather than counting them one by one. I don't know if you've heard of this one, but a gross is 12 times 12. So a dozen, or 144. So if you had like a big box of pencils or something, you're selling pencils in boxes, you might be selling them by the dozen and then by the gross. And it's a way of counting small things in batches. And the mole is the same, it's just a much bigger number. point. So a very, very, very big number. 10 to the 23 means that it's going to be 6. Well, you know what? Let's write it out so you can see. Okay, that's what that number looks like. Can't even fit it all without getting my head in the way. Move it up a little bit. So that's what that number means in scientific notation. It's an extremely large number, but conceptually it means the same thing as these other smaller numbers. It's a way of counting things in batches. And why would we ever need to count something in giant batches like this? Well, when the things that we're counting are extremely small, namely atoms and molecules. Atoms and molecules are so small that on our scale, like what we can actually experience, we have to count them in enormous batches because one atom or even a dozen atoms or a gross of atoms or even a few thousand or even millions of atoms are just too small for us to actually manipulate or do anything with. So we need to get in this massive quantity of atoms or molecules for us to be able to, let's say, measure them, manipulate them, react them, and so on. So this is why we use moles to kind of do our counting when it comes to atoms. So one way we can use these types of numbers is to substitute them in for the actual count. So if we said we had 3 dozen dogs, you could probably think about what that would be in your head, but if we wanted to think of it as a conversion factor, that would be 3 dozen. And then we need to think about how many there are per dozen. So there's 12 dogs per dozen. And so that would be 36 dogs. We cancel that now. So the conversion factor is like the definition of the number. 3 dozen dogs is 3 dozen times 12 dogs per dozen, or 36 dogs. And we don't think of it quite as much with these smaller numbers, but we can also use fractions there. So we could say 3.75 dozen dogs. You know, that may not be as useful, and somebody might be confused because if they didn't know dozens, they'd think you were talking about fractions of a dog. We're not talking about fractions of a dog. We're talking about fractions of a dozen dogs or a batch of dogs. And we can still calculate that in the same way. So 3.75 dozen, and there's still 12 per dozen. And so what's that going to be? Well, 0.75 times 12 is 9. So we'd add an additional 9 dogs on here. You could do that on your calculator. Check me out, make sure I'm right here. But I believe that would be 45 dogs. So a lot of dogs. All right. So now let's move into the mole range here. How many carbon atoms are there in 3.75 moles of carbon atoms? So notice this is the same basic type of question as with our dozens of dogs. But this time, instead of talking about 12 dogs per dozen, we're going to talk about this many carbon atoms per mole. This number, by the way, is called Avogadro's number. So we're talking about that many carbon atoms times however many moles. So this many per mole, that many moles. Let's solve it in the same way. 3.75 moles of carbon atoms. And our conversion factor is going to be how many atoms are there per mole, per 1 mole. And how many anything there is per mole is 6.02 times 10 to the 23rd. So notice that the unit on the top is going to change depending on what you're trying to count, because these numbers are unitless. They're just a counting, a number of something. So this many atoms per mole, it's also this many molecules per mole, it's that many dogs per mole, it's that many whatever you want per mole, whatever you are trying to count in this case. So moles cancel here. We do that multiplication. And now, depending on the calculator you're using, you may or may not be able to deal with this scientific notation. So let's say, like, I don't know if you can see this. This is just my phone, and it's like a regular. Yeah, it's not really coming through. Wait, no, I don't know. You can sort of see it there. It's a regular like 4-function calculator, right? It's just got numbers and then plus, minus, multiply, divide. So how do I do something like scientific notation on a standard calculator like this? Well, what I do is I leave off the exponent here, or the magnitude, the power of 10, and I just multiply 3.75 times 6.02, and I get 22.575 times 10, and then I just stick on that extra part, right? Because multiplication can be done in any order. So we can multiply this times this, then multiply that, and that's fine. Now, if you leave an answer like this, that is totally fine with me, and I have no problem with it. But you should know that in proper scientific notation, you're not supposed to leave more than one number before the decimal place. So if we really wanted to be proper here, we would move the decimal over and compensate by adding to the exponent here. So we could also call this 2.2575 times 10 to the 24th. I mean, that's the same thing. We're just adding another place of 10 to our power of 10. Okay, so now this next question, we should be able to do without any calculation, because here it says how many dogs are there in 3.75 moles of dogs. We already did this question, we just changed the label. So instead of counting carbon atoms, now we're counting dogs, but since the number of moles is the same, the number is going to be the same. So we're still going to have 22.575 times 10 to the 23 dogs. Right? The calculation is going to be exactly the same. The only thing that's changed is the label, where we're looking at dogs per mole instead of atoms per mole. All right. Now let's look at when that changes a little bit. How many moles of dogs would you have if you have 3.64 times 10 to the 26 dog legs? Which is a bizarre question for sure. So again, we don't want to get messed up here. We want to recognize that we are being told something about dog legs. And we want to ultimately know not how many dogs we have, but how many moles of dogs we have. So we actually need a couple conversions here. We need the dogs per mole conversion, or dog legs per mole. But we also need a conversion of how many dog legs per dog. All right, and I know there's various dogs with different numbers of legs out there, but let's, for the sake of the question, assume that dogs have 4 legs per dog. So we're going to have this many dog legs, but we actually have to cancel that unit of dog legs, because what we really want is dogs. That's what we're being asked for. So there's 4 dog legs in each dog. And notice that, if I just said how many dog legs per dog, I would have put 4 dog legs over 1 dog, because that's the more natural way of thinking of that conversion. But when I follow the units, I know I have to cancel dog legs and be left with dogs. So let's do that one first. So that's going to give me 0.91 times 10 to the 26 dogs. Again, I could correct this scientific notation by adjusting it, but I'm just going to leave it. And then we want to know moles. So we go, okay, 0.91 times 10 to the 26th. Oops, I forgot my unit. Sorry. Don't forget your units. So this is dogs. And now I want to convert from dogs to moles. of dogs. And anytime we're converting from a individual count to a count by moles or a count by a batch of them, that's going to give that we're going to use Avogadro's number. So 6.02 times 10 to the 23 dogs. All right, we'll divide those two numbers. So I'm going to divide my 0.91 divided by 6.02. And I'll get 0.15. I'll add another place there, 0.151. And now to get my exponent, since my calculator can't do that, I'm going to look at the two and go, okay, it's 10 to the 26th divided by 10 to the 23. Well, if we're dividing powers of the same base, if we're dividing exponents with the same base, then we just subtract the exponents. So 26 minus 23 is 3. And so that's my answer. And I can make that a little bit nicer. I can move it and go 1.51 times 10 to the 2. Or 151. Those all mean the same thing. If you don't understand that, go back up and review the scientific notation part. Make sure that you have some facility with that, because when we deal with these big numbers, we really have no choice but to use scientific notation. They're just too big to be writing out however many zeros. Even if I could do that, my calculator wouldn't take that many zeros. So, yeah. Okay, now let's move this into the mole and molecule realm. And notice that when we talk about how many atoms are found in a particular number of moles of molecules, we're really doing the same thing as the dogs and the legs. If we want to know how many carbon atoms are found in 0.5 moles of methane molecules, well, we have to know how many carbon atoms are in each methane molecule. And in this case, it's 1. So there's 1 carbon atom per molecule. But then in the question below, how many moles of hydrogen atoms are found in this many methane molecules? Well, now we have to do that thing like the legs again, because there's 4 hydrogen atoms in each methane molecule. So we have to, at some point, multiply by 4, or divide by, depending on how the units work out, 4 hydrogen atoms per methane molecule. So there's another conversion in there to do. All right, so give those a try. Let me know if you get stuck. I'd love to see what you come up with. And now we're going to extend this on to molar mass and multimole ratio. So molar mass is how we measure moles in the lab, because we can't count individual atoms, and we can't even really count moles of atoms, at least not directly, because they're too small. We can't see them, we can't count them easily. So the way that we count things is by weighing them. Just like if we were to, let's say, have a giant box of giant jar of jelly beans or something, and we're running one of those games where you have to guess how many jelly beans are in the jar. Rather than count them all individually, we could take the mass of one jelly bean and then the mass of all of them and divide and figure out how many are in there. And that's what we do with atoms and molecules also. We weigh them, we look at how much an individual mole would weigh, and then we do some division to figure that out. So to find the molar mass, which is the mass of 1 mole, we can actually use the periodic table. So if you're wondering where that weird number comes from, that 6.02 times 10 to the 23rd, this is where it comes from. It's the number that relates the atomic masses that we talked about earlier in the semester, the average atomic mass of, which is the mass of a single atom in AMU, atomic mass units, relates that. So Avogadro's number relates that to grams. So if one atom weighs, for example, 12.011 atomic mass units on average, then 1 mole of that atom So if you have 6.02 times 10 to the 23rd carbon atoms, would weigh 12.011 grams. So we can use that same number now to talk about grams instead of grams of a mole instead of atomic mass units. So for carbon, it's 12.011 grams per 1 mole. Notice I left the E off there. That's the abbreviation for mole. It's not a great abbreviation, but M is meters, MO is months, so that's the best we can do. So the abbreviation for moles is just MOL. Saves us 2 letters. Okay, so for the individual atoms, we just look up the number on the periodic table. That's the mass of 1 mole. For a compound like methane, sorry, I didn't take this off. So there's our mass of 1 mole. Yep. Thank you. Sorry about that. Now you can see it, I think. So there's the mass of 1 mole of carbon. We can write it as a conversion factor like this. In a compound like methane, we would just add those up for all the atoms in the molecule. So carbon is 12.011, hydrogen is 1.01, and there are 4 of them. And so the molar mass of methane is 16.051. So that's grams per mole, grams per 1 mole. So then, now that we have a conversion factor, remember, even though it's grams per mole, it's some new concepts, new ideas. Mathematically, working the problems, it's the same as the unit conversions between, centimeters and meters or whatever we did last night. So how many moles are in 32.10 grams of methane? Well, we could go 32.10 grams of methane, CH4, times our conversion factor, which is going to take, make this a little bigger. Our conversion factor is we're going to cancel the grams and instead have moles. And the conversion that takes us there is our molar mass. So 16.051 grams per 1 mole. Make sure the mass goes with the grams, and mole is going to be 1. So now we divide 32.10 divided by 16.051, and we get, let's see, 1.9998. So we're just going to round that to 2.000 because that's how many significant figures are in the question. And that's how many moles of methane we have here, right? So just a conversion factor. All right, so you can try these other ones that then ask you about some atoms. And the last thing we're going to talk about this morning is mole-to-mole ratio. All right. So again, we're talking about a conversion factor. If you have a certain number of moles in a compound, you can use the conversion factor given by the molecular formula to figure out how many moles of the individual atoms you have. So let's take a look at this first one. You have 2.5 moles of ethanol. How many moles of carbon do you have? Okay, well, ethanol is C2H6O. That's the formula. So we want a conversion factor that takes us from moles of ethanol to moles of just carbon. And that conversion factor is right there in the formula. There are 2 carbon atoms per molecule or per formula unit. So there's 2 of these for every one of these. So then our answer is going to be 5.0 moles of carbon. That's it. That's all it takes. Let's jump down where the numbers get a little bit trickier, but the concept is still the same. You have 6.32 moles of chromium 2 phosphate. Here's the formula for chromium 2 phosphate. How many moles of chromium do you have? Well, we're going to start with that number, 6.32 moles of the whole thing. And we're going to multiply by a conversion factor that takes us from moles of the whole thing to moles of just Cr, just chromium. And that conversion factor is 3 moles of chromium per one of that. So then we can just multiply by 3. Let's jump down and look at oxygen here. So how many moles of oxygen would we have? Well, we got that same basic setup, 6.32 moles of and this time we want moles of oxygen per mole of formula. Everything is really the same. I'll move this up so you can see it. Everything is really the same technique-wise. The only difference here is now the oxygen is inside these parentheses because it's part of this PO4 unit. So there's not 4 oxygens in this formula, there's 8 because there's 2 phosphates, 2 total phosphates. So that gives us 8 oxygen atoms per formula unit. And so we're going to multiply that number by 8 to get that ratio. All right. You can also do this, by the way, with a chemical equation. So if you have a chemical equation and you want to know, well, if I've got 5 moles of this reactant, how many moles of the other reactant do I need? You can figure that out by looking at the coefficients. So the ratio of the coefficients, and that tells you how many moles of the other one you're going to need. So if you encounter some problems like that, that's how that works. So here's some other practice for you. And there's also a practice worksheet on Blackboard. If you want more practice, there is tons of stuff around on this. This is, one of those kind of classic topics of introductory chemistry classes. So if you look up mole practice, or if whatever I'm saying today didn't make any sense to you, you can look up a million other people on YouTube and find other ways of explaining this, of going through it. If you're still stuck and you're struggling with this after you've tried it and practiced and kind of gone over a few times, please let me know, because it is something that will keep coming up throughout the rest of the semester. All right, we'll have to run and get ready for lab today, where I will see half of you there. And the rest of you, the other half, I'll see next week or online on Monday. So thanks, everybody, and I'll see you later.